Yes, so I apologize. I changed the topic of the talk at the last minute. I was planning to talk about something else, but then I thought that Hubert would enjoy this talk more than the other one, so I decided to switch. So let's see. Hopefully, I hope you will like it. So this is going to be about computing entanglement entropies, and so when I was preparing the talk, I was thinking back at my at the good old days here in Saclay. So I did my PhD here in the late 2000s with so under the supervision of Hubert and Jesper, and at that time, you know, we were hearing a lot about entanglement entropies. That was a few years after the works of Pasquale, Calabrese, and John Cardy, and many others. It was also the time of the papers by Lee and Haldane came out. So we were hearing a lot about entanglement. I think people here in Saclay, some of them were working on it, so like Vincent and Grégoire. But many people were a bit suspicious. You know, it was trendy topic coming from abroad. We were hearing many things like, is it really interesting? Is it really deep? You know, it's a quantity that's never going to be measured. As we know now, it's being measured in experiments. But, you know, so people were a bit suspicious. And as a young PhD student, I wasn't really sure this was something that I wanted to study. So I sort of got involved in that business thanks to Jean-Marie, Stéphane, who was my co-office here in the institute, just on the first floor, and we were discussing, and at some point we got some interesting results, and we were really not sure that it was worth publishing, but Hubert's advice and support and was really crucial for us, and he really encouraged us to push this, and that was really important for me. It has influenced very strongly the rest of my scientific trajectory, and I think probably it's true as well for Jean-Marie, although I cannot speak for him. But anyway, these were really good days. I had a wonderful time in Saclay with Hubert, with Jesper. At the time, people who were around were also Constantin Candou, Azat, who's here, was a postdoc here. Roberto Bondesan was my fellow PhD student. Bolage Poshkai was also visiting for a few months. And this was really a wonderful time. Okay, yes, sorry. And so I decided to talk about this just because this is really something that I started, I would say, thanks to Hubert. And also it's a topic that Hubert is also interested in, of course, and he has, although we never published anything on this together, he has worked a lot with other people on this. Of course, Jesper, then also Paolo Zanardi, so his friend and colleague from USC, who is incidentally also going to talk about that later this week. Romain Vasseur, Edouard Boulard, Romain Couvreur, and others. So. All right, so here we are. It's more than a decade later now, and I'm still talking about entanglement entropies. But today it's going to be about operators as opposed to states. So there's a little difference. So let me just give you the definition of this operator entanglement. So as usual, you want to consider, by the way, that stick hasn't changed. It's the one I used in my PhD defense 11 years ago. So anyway, so as usual, you take a bipartition of some Hilbert space. It's a finite dimensional with dimension dA and dB, if you want, just to keep things simple. And then instead of considering a state and looking at the bipartition, looking at the Schmidt decomposition of that state, we want to take an operator acting on H, which is of course just some finite size matrix. And we are asking how far this operator is from a product operator acting on part A and part B. So is it, I mean, depending on the operator we are looking at, we can ask, is it just a product, or do we need two, like a sum of two products to write it, or more do we need more terms? And in general, what we want to look at is some sort of operator Schmidt decomposition that I'm going to write as this. So it's really just like the usual Schmidt decomposition, where here on the right side, the sets of operators in A and B are orthonormal with respect to the Hilbert-Schmidt inner product. And on the left side, I've included explicitly just a normalization factor so that the sum of the coefficients here is 1 squared. So sum of lambda j squared is 1. And now, once I've done this, I can define, as usual, an entropy for the probability measure that is defined by those coefficients. So I can define Rayleigh entropy with the standard formula, and as usual, the limit alpha goes to 1 gives back the von Neumann entropy. So of course this is just the usual definition as usual for the entanglement entropies. It's just that this time we're applying it to operators instead of states. But this is of course nothing but looking at an operator O, which is a matrix of size dA dB times dA dB, as a vector in the larger Hilbert space H tensor H bar. So nothing new at the level of the definition, but it's just that since the objects we are looking at now are operators and not states, you end up looking at different phenomena. So the quantity itself is not different from the usual one. It's just that we are applying it to different objects. So as far as I know, the first people to look at this quantity were Paolo Zanardi and his collaborators. And their motivation initially was something like this. So they were interested in a bipartite system, initially prepared in a product state, and they were asking, let's say that you can apply some unitary operator U. How much entanglement are you typically going to produce between those two subsystems? And they were looking at the following quantity. So they were considering some measure of entanglement between A and B. And they were asking, so starting from a product state, how much entanglement do you produce by applying U? And so they were computing some measure of entanglement averaged over all initial product states. And that defines some quantity called that they were calling entanglement power. And then the question was, does this entanglement power has something to do with operator entanglement as I defined it? And in general, the answer was no. There was no direct relation, but for the Rayleigh 2 entropy, which is sort of the most favorable from a calculational perspective, just because everything is quadratic, then you can actually find some nice formula that they had, where indeed this entanglement power defined in terms of the second Rayleigh entropy does involve the operator entanglement. Anyway, so this is not going to play any role in what I'm going to talk about. It's just to give you some idea of what Zanardi was interested in when he first looked at this quantity. So nowadays, other people are interested in this, and usually it's in relation with the following question. So we are thinking of 1D systems, especially spin chains. And we want to know if we can approximate some operator O by a matrix product operator with reasonably small bond dimension. And this is important for all sorts of computational purposes, because when we can do that, it means we can use MPO or more general tensor network methods, and so there's a huge industry of analyzing this sort of quantities. So the cartoon is the following. So usually what we do is we consider some pure state of the spin chain that in tensor network notations I can represent as this. We look at the bipartition, for instance, half system between two extensive subsystems, and if the entanglement entropy of that pure state is bounded as a function of the subsystem size, then there are theorems that tell us that we can approximate the state by a matrix product state. And this is very efficient for computational purposes again. So now we want to ask the same sort of questions for operators. And the idea is that we look at this quantity, this operator entanglement. If the operator entanglement is bounded, then we are going to say that we can approximate the operator O by a matrix product operator. And of course, this is nothing but saying, again, that the operator O, I can view it as a state in a spin chain that has twice the number of degrees of freedom. So in sort of a double spin chain here, and and then I just compute the normal entanglement entropy of that state, and if this entanglement entropy is bounded, then I can approximate that state by an MPO. So this is the logic. And just a warning, so of course when we do this, so when we treat operators as states in the larger Hilbert space, this means we are always dealing with approximability with respect to the 2 norm, and not with respect to another norm, in particular not with respect to the 1 norm, and this might be problematic for some applications, especially when the operator that you're interested in is the density matrix. But I'm going to ignore that. Okay? Now, okay, so the goal of the talk is just to give you, just to enumerate a few basic facts about this quantity, and to end up with an open problem that maybe Hubert will have some interesting ideas about. I don't know. Okay, so first of all, this is a quantity, not surprisingly, that can be tackled with standard CFT techniques. So the usual multi-sheeted Riemann surface or twist field approach of Pasquale, John Cardy, Olaja, Benjamin, and so on. So imagine you take a critical 1D system with a CFT Hamiltonian H here, and a half system bipartition like this, and you compute the operator entanglement of the evolution operator. So this is something you can do very easily, and you find that it grows that it grows linearly with time. And this is bad news from the point of view of simulability, because it means if you imagine like doing a Trotter decomposition of your evolution operator in a Trotter-like picture like this, so if you want to know whether you're going to be able to approximate that evolution operator by an MPO with a reasonably small bond dimension, then, well, sadly, the answer is no, because because the operator entanglement blows up linearly, therefore this bond dimension will have to blow up exponentially in time. Another very simple result that you can get is if you look at the operator entanglement of the density matrix of a thermal state, in a thermal state. So at finite temperature, so inverse temperature beta, You look again at the operator entanglement for a half system here. And this is again something you can easily compute in CFT. And you find the following result. The operator entanglement is some function of beta. And what's important here is that it doesn't depend on the subsystem size. So it's kind of an area law, meaning that it doesn't depend on the length of the subsystem A or B. So it's bounded as a function of the size. And therefore, that means that if you try to approximate the thermal state by a matrix product operator, then this time it's going to work. So you're going to be able to do that with a bond dimension that will remain not too large. That it will scale with beta, but the scaling will not be too bad. It will be polynomial. And indeed, it's known in the literature that you may approximate the density matrix of finite temperature systems with tensor networks. Okay, so a last simple exercise in CFT. So if you consider a quench in the fashion of Cardi-Calabrese, so you start from some short-range, initial short-range state that you evolve in time. Again, H here is supposed to be the Hamiltonian of a critical system captured by a CFT. And you ask, let's say you ask whether you're going to be able to approximate the reduced density matrix of some interval A by a matrix product operator. So this is not a crazy question, because since the initial state has finite correlations, you know that this is going to be doable at short times. You also know that it's going to be doable at long times, because at long times the reduced density matrix is supposed to go to some Gibbs state, or maybe some generalized Gibbs state, but that generalization doesn't really matter here. So it's going to go to some, let's say, to some Gibbs state. And so this is always also something that you may capture by an MPO. And so then the question is, what happens at intermediate times? And so to answer this question, what we do is that we first trace out the part B to get the reduced density matrix in that system A. And then we cut the system A into two parts. And we compute the operator entanglement for that bipartition A1, so of this guy with respect to this one. And we want to know how this behaves. And so again, the bad news is that it actually blows up at intermediate times. So we see that at small initially, it's also small at long times, as expected. Unfortunately, it blows up in the middle. And so again, this is something you can get easily from some simple CFT calculations, but it's supposed to be more generic, and it's been computed in various other systems. Yeah, you always find the same phenomenon, that there's some sort of barrier at intermediate times. All right, so now I'm going to switch gears and talk about a different kind of problem. So it's still about operator entanglement, but this time it doesn't have anything to do with CFT anymore. Yes? Is
the situation better for gap systems or not gap systems? Sorry.
No, actually it doesn't have much to do with gap.
I think I should repeat the question, sorry. So the question is the situation that you described better for gap systems over gapless systems?
No, in the end, I mean, okay, so I'm talking about this because I did the calculation in the CFT framework first, but the calculation has been done also for other systems, and it doesn't have anything to do with the system being gapped or gapless. It's the same as it's essentially the same as the generic linear growth of state entanglement after a quench. I mean, the calculation was first done by Cardi and Calabrese in the framework of CFT, But it's a completely general conclusion. Yeah. I mean, maybe the specific shape here will change. Yes, and there are results about like in this paper by Zhu. They find a slightly different shape because they're working in chaotic systems and so on. So there are interesting things to say here, but it's in the end it doesn't have to do with gapped whether gapless. It may have to do with integrable versus non-integrable, but. All right, so.
Doesn't it have to do? Doesn't it have to do whether your steady state has a finite correlation length or not? Because there are atypical states which will have infinite correlation lengths in integral models.
Yes, that probably, yeah.
But you were all of these curves were for thermal steady states.
Yeah, these curves are for just, this is a quench from a Néel state in the X exchange, so it's just, I think it's just infinite temperature. Yeah, probably you can find some exceptional cases where it will be different, yeah. All right, so the second thing I wanted to talk about is this, when we apply this, when you compute this quantity, this operator entanglement of initially local operators that are evolving in Heisenberg picture. So that means, I mean, the idea is old and dates back to people who are trying to do DMRG in Heisenberg picture. So their idea was to say, look, we cannot do DMRG for quantum quenches because if we look at if we try to evolve as a pure state, the bond dimension will blow up because the entanglement entropy grows linearly. But we could do something else. Instead of evolving the state and trying to approximate the state at time t by an MPS, we could evolve an operator and try to approximate the operator at time t by an MPO. And then if this is doable, then that's fine, because then we can compute this efficiently and then just compute the expectation value of that operator in a short-range state, and that we would know how to do this. So it's a kind of natural idea, and that people have tried, but somehow it's not entirely clear whether it works or not. So let's attack this through the prism of operator entanglement. So we consider an operator acting on a spin chain that is initially local. So let's take some operator phi acting on a single site, and everywhere else it's just the identity. So again, we think of doing some numerics there, and so we want to evolve that operator in time. So the top side we are going to evolve forward in time. The bottom sides here we are going to evolve backwards. And of course, so we apply several Trotter layers. And of course, since here it's the identity everywhere, we can just contract this network, and we end up with a network that looks like this. And what we want to do is then ask whether the operator entanglement of that part A with respect to part B here is small, or if it blows up in time. X here is, I'm defining X as the distance between the position of the cut between A and B and the initial position of the operator. And so this is a quantity that has been studied, for instance, by Adam and collaborators. So they looked at this quantity in an Ising chain in a chaotic Ising chain, and their claim is that you always find a pyramid shape like this, And in particular, in the middle of the system, this quantity is growing linearly in time. And they have, so this is a numerical result, but they have a whole theory, membrane picture that supports this. So the claim is that if the system is chaotic, then the operator entanglement should grow linearly. On the other hand, there are free fermion calculations that date back to the late 2000s by Prosen and Pigeon that showed that for free fermions, at least, the behavior was different. It's logarithmic in that case. So it seems that something is very different whether the system is chaotic or whether it's integrable, or at least free here. So like 2 years ago, we did some numerics with Vincenzo Alba and Marco Medeniak, and for some other systems. And it seemed that whenever it's integrable, essentially you find something that is at most logarithmic. So, okay, and we were able to support this by some analytical calculations in some toy model, and other works have been have appeared since then, especially by Bruno Bertini and also others that have sort of confirmed that scenario. So it seems that this operator entanglement of Heisenberg operators in Heisenberg picture, it really distinguishes integrable from non-integrable dynamics. So if it's integrable, it seems to grow at most logarithmically. If it's chaotic, then it's linear. So, okay. So I don't think anyone can claim to have proved this, but it seems reasonable, and evidence is accumulating that this is correct. And it's interesting because it's a question you can study with various kinds of toy models and so on. And one very last thing I want to say. This is something I'm working on now, and there's kind of an open question here. So maybe Hubert will have some nice idea. Okay, so we are now looking at dissipative evolution, so Lindblad evolution. So consider a spin chain again. It's, for simplicity, consider just just hardcore bosons with hopping, or XX chain if you prefer. And you look at the density matrix of that system. And let's start again from some initial state that is shortly correlated. So, for instance, an AL state. And the question we ask is, how does the operator entanglement of the density matrix grow? So if you just compute it here for a unitary evolution, of course it has to grow linearly in time. With a slope that is exactly twice the one of the state entanglement. So state entanglement would be here. This is the operator entanglement of the density matrix. This is simply because here the system at any time remains in a pure state because it's unitary evolution, and therefore the operator entanglement is just twice the state entanglement. Okay, very, very simple. But now imagine we just add incoherent creation or annihilation of particles. So we add these Lindblad terms here, which are going to destroy coherence. Then what happens to the operator entanglement? So what we expect to happen is something like this, because so this linear growth here is really due to the fact that we are in a pure state, and so it's something that really depends on the coherence in the system. But after some characteristic time of order 1 over gamma, where gamma is the strength of the dissipation, we expect coherence to be destroyed, and eventually, if the dissipative evolution is generic enough, we expect this to just heat up the system to infinite temperature, and so things should decay exponentially. So we would have, again, some sort of, similarly to the case of the reduced density matrix that I discussed earlier, we have some sort of we have small operator entanglement both at short and long times, but in the middle we have some sort of entanglement barrier. And the question is, I mean, for numerical purposes, the question would then be how high this barrier is in general. And okay, so this is very simple, very simple scenario, but it turns out some people, I mean, it has played some role recently in the context of the claims about quantum supremacy by Google. So you know that two years ago, or 2 or 3 years ago, Google announced that they had reached quantum supremacy. It's a buzzword for saying that they have performed a computation on their quantum computer that cannot be done in a classical computer. And then those people actually, by studying precisely the operator entanglement in a similar fashion, they argued that if you take the Google experiment, so you can think of it as a bunch of qubits that you put like here, and then you apply some gates, and the depth of the circuit here that was implemented by Google, essentially they argue that if you add noise, so the depth here of the circuit is playing the same role as time, as in what I was describing here. And because there is noise in the experiment, the point is that they also say that actually at long times you can describe this thing by a tensor network. And they did some calculations to evaluate the height of that barrier here with the parameters of the experiment, and then they argued that the height was not high enough to justify that it was not doable on a classical computer. Anyway, so this is perhaps not what we are really interested in here, but it's just that it's something that is showing up also in other fields. And finally, you can ask how generic this thing is here. So we've been working with Johannes Schachenmeier and Vincenzo Alba, and they have done numerics with students also, and they've tried all sorts of systems, all sorts of spin chains, also all sorts of dissipators. And there is one case where they found something that was kind of spectacularly different, and that's the case of, again, just hardcore bosons. But this time you put dephasing instead of incoherent addition or suppression of particles. You just put dephasing, and this time the operator entanglement does something like this. So it initially grows, then goes down as before, but then instead of going down exponentially, it starts growing logarithmically in time. And so we are currently trying to understand this. We haven't quite understood it yet, but it's kind of weird. Yes, Fabian, I was expecting that you would ask something.
How is this possible? Because that model has an infinite temperature steady state.
Yes, but in a fixed particle number sector. So the big difference between this and the previous one is that now there is a conserved quantity, which is just particle number. So it's true.
And the steady state is the infinite temperature state.
In a fixed particle number sector. And this has entanglement. If you take a spin chain size 20,
so you prepare it in the initial state where particle number is not conserved.
State. It's the Néel state, so particle number is conserved. Yes, and as you know, the Liouvillean is gapless in that case because you solve the model. So okay, so this model is far from being generic. It's kind of special, and Fabian actually showed that it can be mapped to the Hubbard model in 1D with a complex interaction. So it is special. But these guys who were doing numerics, they didn't fine-tune anything. They just said, okay, let's try. We have tried this this dissipative term. Now let's try this one, and they just observed that for dephasing, something very different happens. Okay, so consider it as an open problem for now. So that's it. So I advertised this quantity, this operator entanglement. I think it's interesting. Again, there's nothing new at the level of the definition. It's just that if the operators that physics gives us are very different from the states that physics gives us, and so you end up asking different kind of questions compared to the good old entanglement entropy. And I think there are some funny surprises with that quantity, and especially this fact that it seems to distinguish chaotic from integrable dynamics, and maybe this logarithmic growth for some special types of dissipative evolution. So happy birthday.